Coulomb's law is the way to find the force on one charge due to another charge. The force is proportional to the product of the charges, and it's inversely proportional to the distance between them squared. So here's two charges. I use big Q for the source charge and little q for the charge we're going to find the force on. And I could label the distance between them as the regular old position vector r. As long as I only have two charges, I could think of big Q being at the origin. And then it's perfectly fine to use the regular old position vector r for that, and it would go from big Q to little q, in this case, if we're finding the force on little q. So I have written the proportional version here. The force is proportional to the charge times the two charges, the product of the two charges. I'm actually going to put, for now, let's start with just the magnitude. There is a way to write the direction as part of the equation, but we'll do that in a minute. You probably already know if the two charges are like charges, so if both capital Q and little q, if they're both the same charge, then they repel each other. So opposites attract and like charges repel. And so if they're the same charge, both positive, then they would repel each other. And the force would be along the line between them, but away from the other one. So this would be the force on little q, and this would be the force on big Q, the direction. So those are two different directions, and so it matters which one of those I'm doing in terms of the direction. Turns out, you probably already know that from the third law, Newton's third law, but the magnitude is actually the same. So Newton's third law says whenever two objects interact, the force, in this case, the force of big Q on little q is equal and opposite to the force of little q on big Q. You can see that in this equation. It doesn't matter which order I write the q's, and of course r squared, also the order doesn't matter there. When a vector squared, it becomes a scalar and the direction doesn't matter. When I replace the equation there with the proportional symbol, when I replace a proportional symbol and make it an equality, the equation becomes, we usually write it with a k for the Coulomb constant, q over r squared. So I replace the proportionality with this constant k. K has a value of 8.99, yes, I'm just going to use 9 most of the time, 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. So 9 times 10 to the 9th. Newton meter squared over Coulomb squared. That makes sense. So the we know the force has to be in newtons, and the K has Newton meter squared over Coulomb squared. The coulombs, there's going to be a coulombs times a coulomb, canceling the Coulomb squared in the denominator of the constant, and then for the r squared there will be meter squared, canceling that, and you'll be left with newtons. So that makes good sense. So we have that equation. Let's do a really quick example. Let's find the force on an electron due to a proton. Find the force on an electron that is 5 times 10 to the minus 11th meters away from a proton. I chose that distance because it's the Bohr radius. So that's a typical distance an electron could be from a proton. So 5 times 10 to the minus 11th meters. That will be our r. So I can use the very similar diagram there. So we have a proton, some distance r from an electron. Those, in this case, these have opposite charges. We're just doing magnitude so far, so I'm not going to worry about that. F equals K. We often use the symbol E for the charge of an electron. So there's two of them, both of them With the magnitude, one of them, the electron would have a charge of minus e, but since I'm putting the magnitude there, it will just be positive k e squared over r squared. Plugging in numbers, 9 times 10 to the 9th Newton meter squared over Coulomb squared times the charge of the electron is something you can look up. It's 1.6 times 10 to the minus 19th coulombs. That will be squared, and the distance I gave was 5 times 10 to the minus 11th meters squared. So as I mentioned, there's a Coulomb squared, cancels a Coulomb squared, and there's a meter squared, cancels this meter squared. The meter's inside the parentheses, so it does indeed get squared. And I worked that all out. I got 9.22 times 10 to the minus 8th newtons. That's a pretty small number. So as you can see, those charges are really small. So times 10 to the minus 19th. So this is really small. You don't have one electron very often in the lab. So more reasonable size of charges would be like microcoulombs or nanocoulombs. That's usually more along the lines of what you have in a typical intro lab setting. Let's talk about the direction. I've already drawn an example where they were both positive, and then I mentioned the electron has a negative. So if I were finding the force on the electron, that direction would be there. So the force on E would be that direction. And opposites attract, the force on the proton would be that direction. So again, two different directions, and you need a way to distinguish that if you want to write the equation as a vector, which we can do. So we had the magnitude version written like this. Doesn't matter which q I put first, r squared. What you can do is, if you had the, oh, I shouldn't erase that picture, I'll redraw the picture. This would be the force on little q. So the force on little q, because of big Q, draw them again, little q, and then this would be my r vector. Our vector goes from big Q to little q. So it goes from the first, I would call that a source charge, from charge big Q towards little q. And then, since when you plug in that one of the, without the magnitude signs this time, you plug in that one of those charges is negative, and that will give you a negative sign, so that the force on little q becomes negative. R hat, if you haven't seen R hat before, R hat is defined as R vector over the magnitude of R vector. It's a unit vector, so you divide the vector by the size, magnitude, and that gives you a vector of length 1, a unit vector. Size, I like to use the word size better than length. Vector of size 1, it is distance in this case, so it's okay to say length, but vector of size 1 in the direction from big Q to little q. Now when we flip that, which is what will happen because we're going to get a minus sign, when we get k times minus e times e without the absolute value signs, that becomes minus k e squared over r squared r hat. And it is a vector now, and it's on little q. So now you have to remember that r goes from the source charge to the charge you want to find the force on. In this case, I'm calling big Q the source charge. It's the one I put at the origin to make r look like the regular old position vector. So if r goes this way, then it absolutely makes sense that having a negative sign, because we said opposites attract, the force on little q is this direction that matches the negative sign that we have right here. So there's the negative sign.